Welcome to the Science Behind. This clip is a portion of the Science Behind Blacksmithing series. Today we're going to focus on the fuel that the blacksmith uses in his forge. By combining his skills and imagination, the blacksmith can create a wide variety of useful items. An important idea for you to know is that a fire is just another example of a chemical reaction. In a chemical reaction, elements or compounds, we use the word reactants to describe them, come together and make contact. They have enough energy to start the reaction, and they're in the correct orientation or shape that allows old bonds to be broken, chemical bonds, or new bonds to form. The breaking of those old bonds or forming of the new bonds can release energy as heat, or sometimes it can draw heat in from the environment so it cools things down. For a fire to burn in our blacksmith's forge, three things must be available. The first is fuel. In our forge, the blacksmith uses low sulfur coal. We'll talk more later about why low sulfur coal. The second thing our forge fire needs is oxygen. Oxygen makes up about 21% of the air that we breathe in and out as we go about our day. The third thing our forge fire requires is a spark. So every morning, the blacksmith, when he comes into work, has to load coal into the forge and then use a lighter to start the fire. Just above the coal kettle is the bellows. The bellows are made of wood and fabric. They expand and draw air from inside the blacksmith shop. And then as they close, they squeeze that air out of the bellows into the nozzle, into the forge. That extra air and the oxygen it carries causes more of the fuel to ignite and start burning. You can see in this short clip that as the blacksmith works the bellows with his left hand, he uses his rod stock, that's the metal he's working on, with his right, put it in the fire and increase the heat of the fire, increasing the flexibility or malleability of the metal.
In another video entitled The Chemistry and Physics of Metalworking, I introduced the idea that all matter in the universe could be broken into smaller and smaller pieces until you reach elements. Elements are groups of atoms that have a series of shared characteristics. So iron has an atomic number of 26. That means there's 26 protons and 26 electrons in every atom of iron. And that combination of electrons, protons, and neutrons results in every atom of iron having a specific melting point, a temperature at which an atom of iron moves from being a solid into a liquid. So most of the time in our everyday life, metals are at temperatures where they're solids. Other elements or compounds like water, which is a mixture of more than one element, at normal room temperature is a liquid. If we add energy or heat to that liquid water, we can eventually make that water evaporate into a gas or change from a liquid to a gas.
So a blacksmith has to be very careful about how much energy or heat or temperature that's contained within his forge fire. Because if he overheats his iron, too many molecules of iron will melt or go from a solid to a liquid. That liquid iron could fall down in the forge or onto the floor of the blacksmith shop, where it would not be useful for him to work on. Too little heat, energy, or temperature on the iron would be so hard, so much of the metal would be a solid, that as he pounded on it with his hammer and on the anvil, the metal would tend to break instead of bend or deform. So he would have a much more difficult time shaping the metal. So one of the real skills of a blacksmith is to be able to look at the hot metal and, based on the color of that metal, determine how soft or how hard that metal. Or what he's really determining is what percentage of the molecules are a solid and what percentage are a liquid. He's trying to go for a semi-solid, something that's solid but also malleable. In the background of this entire video, I've left the blacksmith heating and then working the metal and then reheating the metal and working the metal. That's how the blacksmith spends his day, shaping metal into useful items by controlling how much heat is held within the metal. How does he adjust that heat? He either adds air by pumping the bellow, which forces more air in, or you'll sometimes see him use a small poker to move more fuel into the forge and increase the heat that way. Now, when metalworking was first thought of, the fuel everyone was using was wood. And not all woods are the same. Some things like softwoods, like maybe a pine tree, that wood has a lot of metal in it and less carbon, so it doesn't get as hot. So blacksmiths or metal workers very early on started using hardwoods. They have less water in them and more carbon. And then to make their fuel even more useful, they realized that they would dry the wood and allow some of that moisture to escape. Because when a fuel has water in it, that water is absorbing heat or energy. Eventually, as it gets warm enough, that heat or energy will convert the water from a liquid to a gas. We've all seen water boil as it converts from a liquid to a gas. That means there's less water in the wood, so when the blacksmith uses dried hardwood, he gets a hotter fire. The next step in the development of fuel was charcoal. Charcoal is hardwood that is partially burned, and it's burned under conditions of low oxygen. So a blacksmith would pile up wood, cover it with dirt, and then set it on fire. And the heat would be strong enough to drive off water by converting it from a liquid into a gas in other volatile compounds. Volatile means a small compound that at lower temperatures moves from being a liquid into a gas. So charcoal burns off water and volatiles, and you end up with more and more just carbon left. And that carbon burns at a very even temperature, so it's easier for the blacksmith to control the heat that's in the metal he's working. Many years later, early metal workers realized they could use coal. And coal, we call a fossil fuel, is really plants from a long, long time ago that died and fell into an old swamp. And over time, material covered those dead plants, and temperatures increased, and the plant material, the wood and the leaves, changed chemically, and they became coal that has fewer volatiles and less water in it than wood or charcoal. I mentioned early in this video the blacksmiths like low sulfur coal. Sulfur out in the environment is mostly found as the element SO4 or sulfate. It means it's with every sulfur molecule there's some oxygen nearby. And if you remember, fires need heat, an ignition source, a fuel, and they need oxygen. So if you use high sulfur coal, little extra bits of oxygen are added to the forge from that sulfur as it burns. And it makes the fire get hotter and then colder, hotter and then colder, hotter and then colder. So the blacksmith uses low sulfur coal so that it has a nice steady temperature to his forge fire. So the blacksmith starts off with coal. Here you can see a picture of coal, and it's shiny and dark. And then in the morning he begins the next process. He changes coal to Coke, not Coca-Cola like you drink, but Coke. In this image you can see the coal start to burn, and as it burns, the volatiles and the water comes off and goes out through the vent, so that you and the blacksmith don't have to breathe that gases in. But then the blacksmith goes to the water barrel and starts pouring water on a portion of his coal, and it seals the top of the mound by cooling it off. Inside that mound, destructive distillation, or driving the water and volatiles off the coal, changes the coal to Coke. So at the end of the day, we can get a look at this image. What no longer is the fuel bright and shiny coal, now it's gray and lumpy Coke. That Coke is almost all carbon and burns very long, very hot for the blacksmith. You can even buy some of that Coke. The blacksmith has it hanging by the door of his shop, and he calls it dragon poo, or the leftover material after a long day at the forge.